Hello, everyone, and welcome to Porous Media Time Talks, which is now part of Interpol Young Academy. My name is Kamaljeet Singh, and today I've got in studio with me Arya Massini from Kent University. Unfortunately, other colleagues couldn't join us today. So today we've got a lineup of two excellent presentations. The first one is from Ishaan Markale. He is a PhD student at ETH Zurich and EAWAG, studying post-scale mixing and reactions using a combination of experimental and theory. His background is mainly in fluid dynamics, which he studied in his master's at Kalmar University in Sweden. So today he's going to talk about chemical reactions in partially saturated porous media. Uh, so welcome, Ishaan, and thank you for accepting our invitation. The floor is yours.
Okay, great. Thanks a lot, Kamal, for the introduction, and let's get started. So the title of my talk today is Mixing and Phase Saturation Impact on Chemical Reactions in 3D Porous Media. And just to give a little bit of introduction, what I'm mainly talking about is mixing and reactions in the subsurface. And here, if we look at the subsurface, we see the unsaturated zone and the saturated zone, which is the aquifer. And this shows how the soil can be a very complex environment. And now, if we look specifically at the aquifer, here, what I'm showing in the left figure on the bottom is two fluids mixing inside the aquifer in a two-dimensional system, where the gray color is the solids, and what you can see is that the fluids are mixing more or less homogeneously in the pore space. And however, now if we look at the unsaturated zone, where there is a different phase present, for example, air, which is shown in black color in the right figure, we can see that uh, the flow is very heterogeneous, and this makes these preferential flow paths, which you can see here. And this is the area in which the flow is mainly occurring in this case. And this also depends on the fraction of the pore space which is occupied by the water. In this case, it's called the saturation level, and this has also an effect on flow and transport in this kind of systems. So now, if the mixing fronts are reactive, then what can happen is that chemical gradients can be formed inside these preferential flow paths, and this can cause stretching and deformation of the plume, and this has an impact on chemical reactions. And further, the impact of the third dimension is unknown in these kind of systems. So in this work, the main aim was to study water transported chemical reactions at pore scale in unsaturated porous medium and see the effect of phase saturation on these reactions. And the porous medium that we study is basically is representing a soil system. So just to give you a background on how we actually study this, so the technique that we use is magnetic resonance imaging. And the reason for using this is that it's first of all non-destructive and non-invasive, so there's no need for any tracer particles in order to study these reactions. And it's three-dimensional, so we get three-dimensional maps of reactions inside this pore space that we want to study, and we can image different multiple or different fluid phases as well, and we get a distribution of the concentration inside the porous medium. So in the image that you can see here, we have a cylindrical column in which we place glass beads, which represent the porous medium. There is a resident chemical inside these glass beads, and then the injected chemical is from the bottom, and the flow is from bottom to top, and this whole system is placed inside a MRI magnet, and then we visualize the reaction front moving inside the pore space. So a little bit more about the setup. What the reaction that we used is a catalyst indicator reaction, which is given by this equation here. And the important thing to note is that it's a reduction reaction, so it goes from manganese 3 plus to manganese 2 plus. And how we characterize these reactions is using these two dimensionless numbers, the Peclet number and the Damkohler number. And the rate of reaction for this kind of reaction is quite high, so the Damkohler number is very low. So what that means is that the reaction is driven by mixing and not by the kinetics of the reaction. And the immiscible or the non-wetting phase that we use is a fluorinated hydrocarbon, and this one, it doesn't react with any of the other chemicals that we use. So that's a good thing, that that it doesn't react, and also the fact that it doesn't move along with the phases, so it remains in place inside the porous medium. And we study these reactions over a range of Peclet numbers, Damkohler number, and the saturation level. So before I show you this movie, I would like to say that we measure the intensity of the signal that we received from the magnetic resonance imaging, and using a calibration process, convert that into the concentration of the reactant. And we get spatially and temporally resolved concentration maps which are propagating inside the porous medium. So the blue color that you see here is the immiscible phase, which doesn't move with time. And now I will play the movie, and you will see that the beads are not visible in this case, but you will see the reaction front propagating inside the porous medium. And what you can see was that initially the reaction front is quite stretched, and this is due to the heterogeneity of the pore space. And it forms like a fingering pattern, which you will see again now. Let's wait. Yeah, so this fingering pattern becomes more homogeneous as it moves through the pore space. And these fingers are merging by diffusion, more or less. And yeah, this is why we see a more homogeneous front once the front is quite ahead inside the pore space. And we also see hotspots of some reaction much after the front has passed through. So that means that there is some incomplete mixing, or areas in which the reaction front didn't pass through initially. So it happens much afterwards. So somewhere there, and then maybe you'll notice again. Yeah, there again, and then there again. So this is much after the front has passed through the pore space. And I will come to more on this later. So generally, mixing and chemical reactions are not usually predicted well by the advection dispersion reaction equation, especially at pore scale. So in order to predict this using a theoretical model, we use this Lamella-based model, which is a framework which uses geometrical consideration to upscale pore scale observations to the scale of the domain that we are looking at in this case. And what you can see here, I've shown is a cross section of a front moving through this pore space, and what you can see is that this lamella is a collection of sorry. Yeah, so this mixing interface is a collection of these stretched lamellas, and the effective reaction rate, which is the rate of change of the mass of product in this case, is integrated over the whole interface of this lamella in order to get the effective reaction rate, and that depends on the concentration gradient inside the thickness of this lamella, as well as the area epsilon of this lamella. And this is integrated all over the area pi of this lamella. And I will explain this more in detail now. So, sorry about that. Yeah, so as I said before, we are considering natural systems in which the pore size is more or less 1 millimeter, and the pore velocities vary between 10 to the minus 6 to 10 to the minus 2 millimeters per second. And this is called a shear flow regime. And in this case, it has been shown before that the interface area epsilon varies linearly with time. And what we added here is that we modify this linearly varying interface by adding the saturation level here. And then we estimate the gradient of concentration using the initial concentration of the reactant and the transverse thickness S, which is shown in this figure here. And then gamma is the so-called stretching rate, which depends on the average pore velocity and again the saturation. And S, as I mentioned, is the transverse thickness, which is a competition between stretching and compression. And taking this into account, we get this new expression for the effective reaction rate. And this depends only on physical parameters of the system. And in this figure, what I'm doing is comparing what we get from the experiments to what we get from the models. So the symbols that you see is the experimental data, and the lines is the theoretical model. And what we notice is that initially you get a very non-Fickian behavior. So the scaling of the reaction rate is t to the 1/2. So as I mentioned before, this is not predicted well from the Fickian theory. So the Lamella model is able to capture this effect quite well. And this is mainly, as I showed before, the elongation of the mixing front, which was seen at the initial times, which becomes more homogeneous as you move through the porous medium. Another thing to notice here is that as saturation decreases, you have a lower effective reaction rate, and it takes longer for the reaction to slow down. And we'll come to this in the next slide now. So uh, the solid lines that you see here, they stop when breakthrough occurs. That means that there is the first part of the front is already reaching our visible domain. And what we noticed when we were looking at the experiments was that this rate of change, so this slope alpha of how fast the reaction dies down, is changing with different saturations. And this slope I call as alpha, and this basically controls how fast the reaction is distinguishing inside the porous medium. And as you see here, there is this incomplete mixing, which I mentioned before, which we thought is contributing to the fact that the lower saturation is making the reaction last longer. And this can be seen in this figure here, where we see that as the saturation is reducing, it takes much longer for the reaction to completely extinguish, and this is irrespective of the Berkeley number. And that's my last slide. And as a summary, what I would like to say is that MRI is quite a powerful technique for visualizing flow and reactions. And what we found out was that the Lamella model, which we modified for partially saturated systems, it predicts the reaction rate quite well. And the reaction is quite prolonged as the saturation decreases, mainly due to the incomplete mixing behind the reaction front. And that's it from my side. Thanks a lot. And if you have any questions, please go ahead. Thank you.
Thank you, Ishaan, for this wonderful presentation. I really enjoyed the visuals, and also it was nice to see that the Lamella model can capture the experimental stuff very nicely, which was not actually captured by the Fickin flow. Um, I'll ask people who are watching the presentation, if they have any comments, please type in the comment box on the right hand side. In the meantime, I've got a couple of curiosity based questions.
Yes.
So you said it's a glass bead, so, and the pore sizes is like a 1 millimeter. Do you have any limitations on like going down to smaller pores?
Yes, exactly. So the resolution that you get from MRI is obviously not as great as, let's say, tomography. So we are limited by the size of the glass beads that we can use. And in this case, this was 1 millimeters. Below that, we wouldn't have been able to resolve the pore.
Okay.
Yeah.
And are you thinking about making some sort of heterogeneous porous media, something uh, with the maybe I'm not sure, but let's say with a crushed glass or something like that, uh, to make it more heterogeneous?
I actually haven't thought about that, but that's a good idea. I think it's something to be tried. I think yes, definitely.
Yeah, cool.
Yeah.
I think I really like the presentation. Fantastic.
Yeah.
Uh, Aryan, do you have any questions, or should we?
Yes, thank you, Ishaan, for your wonderful presentation. I got one more question, and I was wondering, can you please tell me a little bit about the time resolution of your imaging?
Yes, so one full 3D scan took about 16 seconds to
16
achieve. So that's
seconds.
why the flow rate that I used was quite small.
Yeah, but that's still quite fast.
Mhm.
So
Yeah, and the total size was 32 by 16 by 16, so it's not that huge.
and what do you think is the biggest challenge when it comes to NMR imaging? Because I have some background in tomography imaging, but I don't have so much experience with 3D NMR.
Yeah, so as I mentioned before, I think one of the, at least for if you want to resolve the pores, then you need quite large glass beads in order to see what's happening inside the pore. So that's one limitation. And then the other thing is limitation of size as well, because because what we could actually measure was only about length of 32 millimeters. So if you want to visualize something longer, then either you need to move the porous medium or move the magnet itself, which is not so easy. So yeah, it's a balance in the end between what you want to see and what is your size limitation and so on.
Okay, and the reconstruction of the data, is that a non-trivial step, or is that something that comes with the software from the manufacturer of your instrument?
So reconstruction comes from the software itself. Yes.
Okay.
But still, you need a lot of post-processing to get nice images. Yes.
Yeah, because the images that you showed were very nice. Thank you.
And for our audience, people might be interested in doing this. Ishaan, can you tell us which software do you use for producing these images?
So the post-processing I did mainly on MATLAB, but then for creating these images, I used a software which was developed here at ETH.
Is it open source
It's
or?
open source. I can send a link afterwards to
No, it's okay for the audience. Maybe you can say what the name is so people can search it. Do you know the name of this, which is available?
Actually, I cannot remember the name right now,
No
but
worries.
I will
Okay.
find it out and put it in the chat. Yes.
Okay, fantastic.
Yeah.
Sounds good. Okay, thank you very much once again, Ishaan, for joining us today and for giving us this
Thanks.
wonderful overview. This is really nice presentation, giving a new scope for using NMR. I know never used it. Like Aryan said, I'm also into tomography. Well, okay, so there's one before we wrap up. There's a question popped up in chat.
Yes.
I hope you don't mind. We'll just quickly go through it.
Mhm.
Since the experiment is from Pu Voi Huang, so he's wondering, since the experiments are performed vertically, does density difference of the fluid pre and post reaction influence the flow pattern?
Yeah. So what we observed was that the density difference was quite small, so it didn't really matter in our case. So
Okay.
yeah, it was more or less the same density, you would say.
Okay. Okay, thank you very much, Ishaan, once again, and we good luck with your work in the future work, and we look forward to your publications.
Yeah, thanks for having me. It was a pleasure. Thank you.
Cheers, thank you. Okay, so we'll move on to our second presentation. Let me put the slides on before before introducing our second speaker. Our second speaker is Dr. Hu Ying, who's Cynthia Research Associate in the School of Minerals and Energy Resources Engineering at the University of New South Wales. She obtained her PhD in petroleum engineering from the same university in 2017. Her research focuses on pore-scale characterization of fractured geological materials to gain insights into the underground fluid flow behavior, such as natural gas, hydrogen, CO2, and groundwater. It's another fantastic and very important research area. Um, Welcome you. Thank you for accepting our invitation, and the floor is yours.
Thank you, Kamal, for your introduction. Hello everyone. My name is Jing. Very appreciate for this opportunity for this Interport Tea Time Talks. Today my talk is about image-based gas flow modeling for fractured geological materials. A little bit backgrounds. X-ray microcity images have been widely applied to obtain the internal structure of the fractured media, and using these 3D images, we can get the petrophysical properties of the rocks. One common way to get these properties is to run direct simulation on the microcity images, such as lattice Boltzmann method, finite volume method. And this kind of method are very accurate, but requires significant computational cost. So there is another way to get these properties, which is to find the topologically representative network to reduce the computational cost. So the most well-known network is the pore network model. Well, this model is working very well for granular porous media. However, for the fractured media, there is another network called fractured pipe network. And this is proposed for the fractured media, but unlike pore network model, this model is generally created stochastically, cannot be created based on the microcity images. So my work aims to extract fracture network based on the real fracture rocks, and also to simulate multi-physics gas flow in the fractured media with much less CPU expenses. In this work, I will take a coal sample as an example. The coal rocks consist of the fracture network and also macropores in the matrix. Because they have the gas flows within the fractures and the macropores will have different physical phenomena. So I will characterize the fracture network as well as the matrix macropores separately. For the fracture network, I will apply the pipe network that I mentioned before, in case someone is not really familiar with this network. So each fracture is simplified with a pipe, and they are connected by connecting the center of the fractures with the midpoint of the intersection lines between the fractures. And unlike the conventional pipe network, my pipe network is constructed based on the fracture information that I measured from microcity images, including the fracture centers, orientations, fracture size, aperture, and also the surface roughness of the fractures. And then for the matrix macropores, I will create a matrix lattice network to represent those matrix. And then I connect the pipe network with the matrix lattice network with interconnecting pipes. And then I can have the fracture macropore network model, which is showing in this figure. As I have said, because gas flow in the fractures and macropores will have different physics. So, for example, for the macropore of the core matrix, the flow will have both viscous flow and Nielsen diffusion. So that's why for the conductance of the macro throat elements, the conductance equation includes Hogan-Poiseuille equation as well as the Nielsen diffusion term. And for the fracture pipes, I've just applied the cubic law. And for the interconnecting pipes, which connecting the matrix and the fracture network, because this pipe is only for mass transfer, there is no flow resistance. So I just give a random high value for the conductance. Because most fracture network is mineralized, so my model will also determine if the fracture is mineralized or not. If it is, what type of mineralization it belongs to. There are commonly two types of mineralized fractures. One is as shown in figure B. The fracture is fully mineralized. So for this type of fracture, the hydraulic aperture is significantly reduced, and then I need to change the aperture in the conductance equation for the pipe network, for the pipe element. Well, there is another type of mineralization is the mineral only occupy part of the fracture. In this one, the effective cross area of the flow is reduced. That's for this one, I will have to adjust the A in the equation. So this is governing equations. I have one additional term which account for the volumetric change due to sorption and volumetric change due to compression. So these are the examples of two FMPNM models I created based on the two microcity images on the left. As you can see, those models can capture the fracture network connectivity quite accurately. So this model can be used to get the permeability estimation efficiently and accurately. Table 1 shows the permeability results of both FMPNM model and the microcity images. So result shows me that the permeability are quite close, but with less CPU time. So another, this model can also be used to simulate multiphysics gas flow in fractured media, including viscous flow, gas diffusion, gas sorption. It can be easily applied for multi-phase flow as well. So in conclusion, apart from this two advantages that I mentioned before, this model can also provide an efficient framework for further studies about co-deformation induced by sorption as well as stress conditions. And we can also add micropore heterogeneously easily in the model. Because time is very limited, so I hope my presentation is clear enough. And if you have any questions, you can email me or connect me on the LinkedIn. And thank you very much.
Thank you very much, Ying, for your very interesting presentation. Again, if the audience has any questions, please type them into the YouTube chat, and we will read it to the speaker. While our audience is typing in questions, I have a couple of questions for you as well. And I was wondering, how did you include the surface roughness in your model? You say that you measured this from micro-CT imaging. Was your resolution of your micro-CT imaging enough to really capture the surface roughness of these cores?
Yeah, that's a good question. For this model, the resolution is 4 microns, because roughness is more like it's fractal surface, so it really depends on the resolution. Yes, but what I can do, so I cannot do more based on this resolution, but I can still measure the roughness. The roughness is described by the height of the surface and also the wavelength. So these two parameters will be included in the roughness factor in the equation here. So CF. Okay.
So then it might be possible to also include information from other sources like AFM or so when you more accurately can measure surface roughness and surface area into your model.
Yes. I actually have that roughness factor, but I didn't put here because I don't want to have much more too much details here. Yeah.
That's very good. I saw that in the meantime, we got a question from the audience. It's Abdul Rahman. Thank you for your presentation. And he wants to ask, how do you include the matrix fracture exchange term in such modeling?
as you can see, the fracture model is connected with core matrix model via the interconnecting pipe, which is the blue one. So this pipe is for mass transfer to connecting these two simulations.
Okay, thank you. Now, maybe you, Kamal, have a question as well?
Just curiosity question. If I have not missed it during presentation, I'm sorry if I missed it. I think in terms of have you compared this with the permeability? Because I think what you mentioned, you comparing the permeability. Is it compared with any measured permeability, or is from the simulation work only? From the
Yeah, it's for the simulation only.
Okay. Is there any chance that you would be able to measure it, and then it's a sort of like more towards validation into
Yeah. You mean compare with the experimental results?
Yeah, I was just curious.
Yeah. So in my most recent paper, where I applied domain decomposition methods, because for the real sample, the microcity images is quite large. So for that large image data set, my current algorithm is still very slow when extracting the network. So in my research work, I applied domain decomposition to get this network from larger image set, and in that way it is possible to get the permeability from the lab scale samples, and then I can run the core flooding and get the permeability and do the comparison.
And when you say large sample, so what's the size of the sample you're talking about?
Like 1 inch in diameter and 1.5 inch in length.
Okay, well, fantastic. I think thank you for giving these details, and I think I'll be curious also in the future if we can do sort of for multi-phase flow with matrix fracture exchange. I think that would be fantastic.
Yeah.
Okay, I think that's it. Thank you, Arin.
Yes. All right. Thank you very much, Ying, for your presentation and your questions. And with that, we come to the end of this session, unless there's more questions from the audience, but I don't see them at the moment. If you have any questions, please type them into it after this streaming. You can type always your question in the comments of this video, and then I will pass them on to the speakers of today, if you would like. So with that, I would like to close the session, but not before I have announced the speakers for our next session, which will be in 2 weeks on the 21st of September. This time we'll be streaming a little bit later than usual at 4:30 p.m. Central European Summertime. This is to accommodate a speaker in the United States. So our 2 speakers will be Olivier Vincent from CNRS in France. He will talk about fluid flow in plants. And Ting Xiao from the University of Utah, which will be on geological sequestration of CO2. We very much look forward to see you again in 2 weeks then. And please support our channel by liking this video and subscribing to the channel. That means a lot to us. So thank you very much, and we look forward to see you again soon. Goodbye.
Thank you. Bye.